Particle physics is basically like a quest to figure out what the universe's tiniest building blocks are, the smallest pieces of matter, and the forces that make them do what they do.
Yeah, exactly. It's like figuring out the Lego pieces that build everything we see, stars, planets, even us. And the cool thing is, it's not just some theoretical thing. There are these crazy experiments in technologies, and they have real-world uses.
Definitely. It's where abstract ideas meet like really advanced engineering, and then they actually end up impacting our lives in ways you wouldn't expect.
So, okay, first big question from the podcast. How do we even know these particles exist if we can't see them?
Well, that's where the ingenuity comes in, right? Scientists have developed these super sophisticated detectors. They use indirect evidence, like a detective using footprints and fingerprints to crack a case.
Oh, I get it. So it's like these particles are leaving clues, and scientists are using these detectors to solve the mystery.
Exactly. One of the main methods is ionization. When a charged particle, like a tiny speeding bullet, goes through a detector, it can knock electrons off atoms. That creates ions, which we can detect, and that leaves a trace of where the particle went.
So it's like the particle leaves a trail of breadcrumbs, and the detector's following the trail.
Perfect analogy. There's also scintillation. Some materials actually give off light when a particle passes through them. Like, picture a tiny meteor streaking through the night sky, leaving a glowing trail.
Wow, that's beautiful. So we have ionization, where it's a trail of ions, and then scintillation, where it's like a burst of light. Are there other ways to detect these sneaky particles?
There's also Cherenkov radiation. This happens when a charged particle goes faster than light can in a specific material. It's kind of like a sonic boom, but instead of sound, it's light that's given off.
Okay, so we've got ionization, scintillation, and Cherenkov radiation. Three ways these particles can kind of show themselves, but how do scientists actually pick up these signals? They're probably pretty faint, right? The podcast mentioned something called photomultiplier tubes, or PMTs, I think. They sound important.
Oh, they're super important. PMTs are incredible. Imagine a single photon, a tiny, tiny packet of light. It hits the PMT, and this one little photon triggers a cascade of electrons, and then each of those electrons releases even more electrons. So it amplifies the signal until it's strong enough to be measured.
Whoa, that's amazing. It's like this chain reaction, taking a whisper of light and turning it into this huge shout. But I'm curious, how does that amplifying thing actually work with the electrons and all?
It's all about these things called dinodes. They're electrodes, but they're coated with this special material that easily releases electrons when a photon or another electron hits it. Each dynode has a higher voltage than the one before it, so as the electrons get released, they get pulled towards the next dynode. They pick up energy, hit it, release even more electrons. It's this amazing cascade multiplying the signal until it reaches the anode at the end, and that's where it gets collected as a current we can measure.
So each dynode is like a step on a staircase,
Yeah.
and the electrons are like gaining speed as they climb higher and higher, and then at the top, boom, a strong signal.
Exactly. A great way to picture it. And there's another technology that's becoming more and more popular, silicon photomultipliers. So PMs.
Yeah.
They're smaller, don't need as much voltage, and magnetic fields don't mess them up. They're a fantastic alternative.
So PMs are like the new, improved version of PMTs.
Yeah.
Same abilities, but sleeker and more versatile. But why should we care about all this detector tech? What's the impact in the real world?
Ugh, great question. These detectors aren't just for theory. They have a big impact on different fields. Take PE scans, for example, used a lot in medicine. They use positrons, the antimatter version of electrons. And guess what? Detecting those positrons uses the same principles we've been talking about.
Wow, so this tech designed to study the universe's tiniest things is helping doctors diagnose and treat people. That's wild. It really shows how basic research can have these amazing, unexpected benefits.
Exactly. And it's not just medicine. These detectors have uses in materials, science, information technology, even security, like detecting radioactive material. The influence of particle physics is huge, and it's always growing.
All right, so we've got these particles, we can detect them, but how do scientists actually study them in detail? The podcast mentions particle accelerators. They sound pretty intense.
They are. Imagine this for your presentation. You want to see what's inside a watch, but you can't open it, so you smash it against a wall and study the pieces. That's basically what particle accelerators do.
Okay, I see the analogy, but I'm guessing it's a bit more sophisticated than just smashing a watch.
Oh yeah, way more sophisticated. We've come a long way from early cyclotrons, which were basically like particle merry-go-rounds. They used magnetic fields to get particles spinning faster and faster in a spiral.
Merry-go-rounds. That's a fun way to think about it. So what kind of accelerators are we talking about today?
Well, now we have these huge colliders like the Large Hadron Collider, or LHC, at CERN.
Ah, the LHC. I've heard of that. Isn't that the one that found the Higgs boson?
That's the one. A 27-kilometer underground ring where protons get smashed together almost at the speed of light. The Higgs boson discovery was huge. It's a particle that gives mass to other particles.
27 kilometers. That's like running a marathon underground. Can't even imagine the engineering that went into that. But why all that trouble? Why are these high-energy collisions so important for studying particles?
Well, think of it this way. It's like recreating the conditions that were around right after the Big Bang. Smashing things together at those crazy high energies, you can make new particles. And then you can see what they do, how they act. It's like getting a glimpse into the basic forces and building blocks of the universe.
So by basically recreating the Big Bang in miniature, we're learning about the very essence of reality. Mind-blowing. The scale of these experiments is incredible. I'd definitely emphasize that if I were giving a presentation.
Definitely a great point. Imagine telling your audience that the LHC isn't just some machine. It's like this incredible example of what humans can do, our desire to understand things. It's the result of decades of work. Thousands of scientists and engineers all over the world working together.
It really is inspiring. Makes me even more curious about what these experiments are showing us. Okay, we've got these particles, we know how to detect them, and we can smash them together. But what are the big questions particle physicists are trying to answer?
One of the biggest ones is about dark matter and dark energy. We can only guess they exist because of their gravitational effects on stuff we can see.
Wait, so most of the universe is made of things we can't see? That's a little creepy, isn't it? How do we even know it's there if we can't see it?
That's the tough part. It's like you know a strong wind is blowing because the trees are swaying, but you can't see the wind itself. We see the effects of dark matter and dark energy, but we don't know what they are, how they work, or how they interact with everything else.
Okay, so particle physics is on the hunt for these, like, cosmic ghosts, these invisible forces shaping the universe. What else are they trying to figure out?
Another big mystery is antimatter. Every particle has an antiparticle with the opposite charge. When they meet, they annihilate each other. Big burst of energy.
So it's like this mirror image of the particle world, but with opposite charges. That's crazy.
It is, but here's the thing. There's way more matter in the universe than antimatter, and nobody knows why. It's one of the biggest unsolved problems in cosmology.
So where'd all the antimatter go? Sounds like a cosmic whodunit. And particle physicists are the detectives.
Exactly. And then there are neutrinos. Tiny, sneaky particles that can basically pass through anything. They might be the key to understanding some of the biggest puzzles about the universe.
Neutrinos are like the ninjas of the particle world. Stealthy, mysterious, and potentially very powerful. Okay, I'm noticing a theme here. Particle physics is full of mysteries, but there's got to be some kind of framework to make sense of it all, right? The podcast mentioned something called the Standard Model.
Yes, the Standard Model is like our best understanding of particle physics right now. It's kind of like the periodic table, but for fundamental particles. Lists all the ones we know and the forces that govern them.
That was pretty complete.
You
So
saw.
are we done with particle physics then? All solved.
Not quite. The Standard Model has been incredibly successful. It explains a lot of things, and it's been right in predicting what experiments would show. But it has limits. It's like having a map, but with some blank spots. We know a lot, but there's still so much we don't know.
So the Standard Model is like a work in progress, a map that's always getting updated. What are some of those blank spots, the things it can't explain?
Well, for one, it doesn't include gravity. We still haven't found a good way to fit gravity into the Standard Model, like
Yeah.
having a city map that doesn't show any bridges or tunnels.
So one of the basic forces of nature is missing from our basic model of physics.
Mm-hmm.
That's a big gap.
It is one of the biggest challenges for physicists today. Also, the Standard Model can't explain dark matter or dark energy. Remember, those make up most of the universe.
So those blank spots on the map, they might actually represent huge uncharted territories in our understanding of the universe. It's like realizing whole continents are missing from our world map.
Exactly. And there are other things too. Why more matter than antimatter? Do neutrinos act exactly as the standard model says? So many questions.
I'm starting to get why particle physics is so fascinating. It's not just about memorizing facts. It's about exploring the unknown and pushing the limits of what we know.
Exactly. It's a journey of discovery, always trying to uncover the deepest secrets the universe holds. And it's a journey that involves everyone, really. It's a global effort. Scientists from all over the world working together to build and run these amazing experiments.
It's really inspiring to think about. It's like a reminder that even when the world feels divided, science can bring people together, everyone working towards a common goal.
That's a great way to put it. One of the best examples of that is CERN, the European Organization for Nuclear Research. That's where the LHC is. Thousands of researchers from over 100 countries all working together.
CERN, I've heard of that. Isn't that also where they invented the World Wide Web? Pretty crazy to think that the technology that connects us all came from particle physics research.
It did. Tim Berners-Lee, a British scientist at CERN, came up with the World Wide Web back in 1989. He wanted a way for researchers to share information easily across the globe. Perfect example of how research into something fundamental can have these unexpected, huge benefits that reach far beyond science itself.
It's a great story. It shows that particle physics isn't just about abstract theories. It's about pushing the boundaries of what we can do with technology, and those advancements can have a ripple effect throughout society.
Absolutely. And speaking of reaching a wider audience, science communication is super important in particle physics. Documentaries like Particle Fever do a great job of capturing the excitement, the drama of scientific discovery, and making it accessible to everyone.
I've seen Particle Fever, such a good movie. It really shows the passion, the people behind these experiments.
Exactly. It shows how important it is to make science understandable for everyone. These discoveries belong to everyone, and understanding them can make us appreciate the world in a whole new way.
So true. You don't have to be a physicist to learn about the building blocks of the universe. It sparks curiosity and a sense of wonder. It's about connecting with the bigger picture, where we fit in this whole vast cosmos.
I love that. It's about feeling awe, appreciation for the beauty and complexity of the universe, recognizing how incredible it is that humans are even able to unravel these mysteries.
Well said. Okay, so to sum up, particle physics is this journey of exploration, trying to understand the most fundamental pieces of the universe and how they work. It's a field that's full of mysteries, but also full of wonder and inspiration.
Couldn't have said it better myself. It's also a field that never stops evolving. New discoveries and challenges are always popping up.
So in this first part of our deep dive, we've covered a lot. Those tiny particles, the amazing detectors we use to study them, and those mind-blowing particle accelerators that smash them together at almost the speed of light. We've also looked at the standard model, what it's good at, what its limits are. And then there are the mysteries of dark matter, antimatter, and those sneaky neutrinos.
And as we go on, I want you to remember this journey of discovery is far from over. There are so many questions left to answer. Who knows what groundbreaking discoveries are waiting for us out there?
That's right. The universe is vast, and particle physics is like our key to unlocking its secrets. Stay tuned, because in the next part, we're diving even deeper into this fascinating world. We'll be looking at the cutting edge of research and what the future holds for this incredible field.
We'll be talking about the technology that's pushing the limits of what we can see and measure, the global collaboration of scientists, and the potential for particle physics to totally revolutionize how we understand the cosmos.
And who knows, maybe we'll even find some answers to those mind-blowing mysteries that keep particle physicists up at night. Until then, keep those neurons firing. We'll see you for part 2. I'm still thinking about those blank spots on the standard model map. It's exciting, but it's also a bit scary to think about how much we don't know. But I'm definitely ready to hear more about what's happening at the cutting edge of research.
Excellent. That's exactly where we're headed, exploring the frontiers of particle physics. New discoveries are always happening, and they're constantly changing how we understand the universe.
Sounds good. The source material mentions Hamamatsu photonics quite a bit. What's their role in all this? Are they, like, the rock stars of particle physics detectors?
They're definitely major players. They specialize in light detection technologies, which are essential for particle physics experiments.
Light detection. But we were talking about smashing particles together at crazy speeds. Where does light come in?
It's all connected. Remember the different ways to detect particles we talked about? Ionization, scintillation, Cherenkov radiation. Well, a lot of modern detectors actually convert those signals into light, which is then detected and amplified by things like photomultiplier tubes, or PMTs, and silicon photomultipliers, or SIPMs.
Right. Those devices use light to detect the particles, and Hamamatsu makes those, right?
Exactly. They're known for making really high-quality PMTs and CPMs used in experiments all over the world. You'll find their technology in the huge detectors at the LHC, in neutrino observatories buried deep underground, even in dark matter experiments.
Wow, so they're playing a part in solving some of the biggest mysteries out there. It's amazing to think something as simple as detecting light is so crucial to understanding, like, the very nature of reality.
It really is. And Hamatsu isn't just keeping up with particle physics, they're actually pushing the field forward with new innovations all the time. They're developing better and better photon detectors, ones that are more sensitive, have better timing resolution, and can even withstand those intense radiation environments you find in particle accelerators.
So they're not just providing the tools, they're working right alongside researchers to create the next generation of detectors. That's impressive.
Definitely. Collaboration is key to what they do. They work closely with research institutions, international collaborations, to make sure their devices are tailored to the specific needs of each experiment. So scientists always have the best tools for their groundbreaking work.
It's like they're part of the team, helping scientists get a glimpse of that hidden particle world. And it sounds like their contributions have been really important. The podcast mentioned that Hamamatsu PMTs played a crucial role in the Super-Kamiokande experiment in Japan, the one that found evidence for neutrino oscillations. That was a huge discovery, even won a Nobel Prize in 2015.
Exactly. Super-Kamiokande is this massive detector buried underground, filled with ultra-pure water. When a neutrino interacts with a water molecule, it can produce a tiny flash of light, and that's picked up by thousands of PMTs lining the detector's walls. And by analyzing these light patterns, scientists can figure out what type of neutrino it was, what its energy was, which gives us all sorts of insights into the nature of these mysterious particles.
Sounds like a mind-blowing combination of engineering and scientific genius. Okay, so Hamatsu's got the detector side covered. What about particle accelerators themselves? Are we just going to keep building bigger and bigger colliders to smash things at even higher energies?
That's the dream for a lot of physicists. There are some big plans out there. Physicists always want to push the limits, and they're already talking about next-generation colliders that would make the LHC look tiny.
Bigger than the LHC. I can barely imagine that. What would they be like, and what are they hoping to find?
Well, there are a few ideas being tossed around. One is the Future Circular Collider, or FCC. It would be at CERN, 100 kilometers in circumference, over 3 times bigger than the LHC. And it could reach collision energies of up to 100 TeV. That's 10 times higher than what the LHC can do now.
A 100-kilometer collider. It's hard to even wrap my head around that. Like a particle accelerator the size of a small city.
hmm
The engineering alone must be insane.
Oh, it would be unprecedented. We'd need major advances in magnet technology, cryogenics, vacuum systems. But the scientific potential, it's huge. At those energies, we might discover completely new particles, new forces, things we haven't even dreamed of yet.
Like opening a door to a whole new realm of physics, right?
Yeah.
Revealing these hidden layers of reality that we never knew existed.
Yeah.
Are there other ideas out there, too? Other directions particle physics could go in?
There's also the Compact Linear Collider, or CLIC. As the name suggests, it would be linear. The particle beams would travel in a straight line instead of a circle. This design has some advantages for studying certain types of particles, like the Higgs boson.
So the FCC is all about brute force, smashing things together at crazy high energies to see what pops out. But CLIC is more about precision, zooming in on specific interactions and measuring them with incredible detail.
That's a great way to put it. FCC is like using a sledgehammer to crack open a rock, while CLIC is like using a microscope to study the individual crystals inside. Both approaches are valuable. We need both to really understand the universe.
And there's the International Linear Collider, or ILC, too, right? a proposed linear collider in Japan, specifically for studying the Higgs boson in even more detail. It seems like there's a lot of interest in really understanding this particle.
Definitely. The Higgs boson is a critical piece of the Standard Model. Scientists want to know if it behaves exactly as the theory predicts, or if there are any deviations. If there are, it could point to new physics, stuff beyond the Standard Model.
So it's like we found a key piece of the puzzle, but now we need to examine it from every angle to see how it fits into the bigger picture. It's an exciting time to be following this field with all these new tools to probe the secrets of the universe.
Absolutely. And it's not just about the machines themselves. There are also huge advances in computing power and data analysis that's changing the way we interpret the massive amounts of data these experiments generate.
So it's like this combination of brute force and brain power, pushing the limits of what we can do experimentally, but also how we analyze and understand the data we collect. That's pretty powerful.
It is. With all these advances, who knows what we'll discover next? Maybe evidence for supersymmetry? That's a theory predicting a partner particle for every known particle. Or maybe we'll finally understand dark matter and dark energy, solve some of the biggest mysteries in cosmology.
Or maybe we'll find something completely unexpected, something that changes everything we thought we knew. It's that sense of the unknown that makes particle physics so captivating.
Exactly. It's a constant journey, always new discoveries, and we never know what's around the corner. But one thing's for sure, particle physics is leading the way. It's pushing the boundaries of knowledge and making us ask the really big questions.
It's definitely an exciting time to be following all this. I'm excited to see what the future holds, what amazing discoveries are still out there. But before we get carried away with the future, let's bring it back to the present. You mentioned that Hamamatsu Photonics is involved in dark matter research too. Can you tell me more about that?
Of course, dark matter, as we talked about, is one of the biggest mysteries in physics. It makes up something like 85% of all the matter in the universe, but we can't see it directly. We only know it's there because of how it affects the gravity of things we can see.
Like a cosmic shadow, right?
Yeah.
It's there, it's having an effect, but we can't actually see it. It's kind of freaky to think that most of the universe is made of something we don't understand.
It is. And scientists are trying lots of different ways to detect dark matter particles. One way is to build these incredibly sensitive detectors buried deep underground. They're shielded from cosmic rays and other interference, so they can just wait for a dark matter particle to interact with the detector material.
Like a high-tech treasure hunt, searching for the tiniest signal from this hidden part of the universe. How does Hamamatsu Photonics fit into these dark matter experiments?
They're essential. They develop PMTs and PSIPMs that are sensitive enough to pick up even the tiniest flashes of light that might happen when a dark matter particle interacts with the detector. Remember, we can't see dark matter directly, but these interactions can create faint signals, and we can detect those with the right tools.
So they're helping us see the invisible, to capture these glimpses of something that's been hiding for so long. It's incredible how they're using these advanced detectors to probe some of the universe's biggest mysteries. But dark matter isn't the only puzzle out there, right? What about antimatter? Where did it all go?
Ah, yes, the antimatter mystery. We talked about how every particle has an antiparticle with the opposite charge, and when they meet, they annihilate each other, releasing a burst of energy. You'd think there'd be equal amounts of matter and antimatter in the universe, wouldn't you?
It would make sense. A perfectly balanced universe. Matter and antimatter in perfect harmony. But that's not what we see at all.
Not even close. The universe we can see is almost all matter, and we have no idea why. It's one of the biggest unsolved problems in cosmology, really challenges our understanding of how physics works at a fundamental level.
So particle physics is on a quest to find out where all the missing antimatter went, like a cosmic detective story, searching for clues to explain this massive imbalance.
Exactly. Scientists are studying the properties of antimatter very carefully, looking for tiny differences between matter and antimatter that could explain this imbalance. And CERN is one of the main places this research is happening.
CERN again, always at the forefront.
Yeah.
What kind of antimatter experiments are they doing there?
They have something called the antiproton decelerator. It creates and studies antimatter particles, specifically antiprotons. By slowing these antiprotons down, they can make very precise measurements of their properties and compare them to protons.
So they're basically making a mirror image of the particle world and looking for any cracks in the reflection. Any tiny differences that might explain why matter ended up dominating over antimatter in the early universe?
That's a great way to put it. These experiments are giving us valuable information about antimatter and what it was doing in the early universe. For example, they've managed to create antihydrogen atoms, the antimatter version of hydrogen, and study how they behave.
It's wild that we can create and study antimatter in a lab, considering how rare it is in the universe. It's like holding a piece of the cosmic puzzle in our hands, trying to figure out where it fits.
Exactly. And these studies aren't just about solving mysteries. They have potential applications in other fields, like medicine. We talked about antimatter being used in PET scans, and there might be other medical uses in the future.
So even while we're looking back at the universe's past, we're also developing technologies that could really benefit people in the future.
Yeah.
It's a great example of how fundamental research can have these amazing and unexpected applications.
Absolutely. Research like this often leads to benefits far beyond the original goals. It's a testament to human curiosity and our drive to explore the unknown, even if we don't see an immediate practical use.
Well said. So we've covered a lot of ground here. Hamamatsu photonics, plans for future colliders, research into dark matter and antimatter. But what about those neutrinos? We can't forget about them. They're still one of the biggest mysteries out there, right?
Absolutely not. Neutrinos are incredibly fascinating and mysterious. They're tiny, they have no electric charge, and they barely interact with matter at all. They're like cosmic ghosts, passing through us and everything else all the time without us even noticing.
So they're the ultimate stealth particles,
Yeah.
almost impossible to detect, but they're everywhere, constantly bombarding us from every direction.
Exactly. And even though they're so hard to detect, they play a big role in lots of astrophysical events. Supernova explosions, the evolution of the early universe, they're all influenced by neutrinos.
So even though they're hard to catch, they're super important to understand if we want to get the big picture of how the universe works.
Right. Scientists are building these amazing detectors, often deep underground or underwater, just to try and catch those rare moments when a neutrino actually bumps into an atom. They're like these giant nets cast out to catch these elusive particles.
It sounds like trying to catch a snowflake on your tongue in a blizzard. Must take a lot of patience and ingenuity.
It does, and these experiments have actually led to some big discoveries. For example, they've shown that neutrinos actually have mass. That was a surprise because the standard model originally said they were massless. This discovery has really shaken up our understanding of particle physics and opened up new avenues for research.
So neutrinos are shaking things up, throwing a wrench into our neat theories. They're not behaving like we thought they would, which means something else is going on.
Exactly. That's what makes them so exciting. They could be the key to unlocking new physics beyond the standard model. They might help us understand why there's more matter than antimatter, or maybe they're even a form of dark matter themselves. Who knows?
Okay, I'm sensing a pattern here. Particle physics is full of surprises, and neutrinos are at the heart of a lot of them. Their strange behavior challenges what we thought we knew and forces us to rethink things.
They do. And research on neutrinos is only getting more exciting. There are new experiments coming online all the time. One example is the Deep Underground Neutrino Experiment, or DVUNE. They're going to send a beam of neutrinos from Fermilab in Illinois to a detector 800 miles away in South Dakota.
800 miles. That's a long way for a tiny neutrino to travel. What are they hoping to learn from that?
TINU is going to study how neutrinos change their flavor over that long distance. There are three types of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos, and they can actually transform into each other as they travel.
So it's like a neutrino identity crisis. They're constantly changing their masks as they fly through the universe.
Uh-huh. Yeah, that's a great way to put it. By studying how they oscillate, scientists hope to learn more about their basic properties and how they affect the universe. DNUNI will also look for differences between how neutrinos and antineutrinos oscillate, which should help explain that matter-antimatter imbalance we were talking about.
So DONE is like this giant neutrino telescope, looking deep into the heart of these mysterious particles. The scale of the experiment and the potential for new discoveries is just incredible.
It is. It's one of the most ambitious neutrino experiments ever, and it could completely change how we understand these particles and their role in the universe.
This has been an amazing journey so far. We started with the basics of particle physics, and now we're exploring the frontiers of research, these big mysteries of dark matter, antimatter, and neutrinos. We talked about the technology, the collaboration of scientists around the world, and the potential for huge discoveries that could rewrite the textbooks.
It has been an amazing exploration, and I'm so glad we could share it with you. But there's so much more to discover. The future of particle physics is wide open. As we keep pushing the boundaries, we're bound to find even more surprises and challenges. But that's what makes this field so exciting.
Absolutely. And in the final part of our deep dive, we'll change gears a bit and look at the human side of particle physics, the passion, the dedication, the collaboration that makes this field so special. We'll also talk about the importance of communicating science and reaching a wider audience.
Because particle physics isn't just about equations and experiments. It's about understanding the universe and sharing that wonder with everyone, inspiring future scientists and helping people appreciate the role science plays in our lives.
I love that. It's about connecting with the bigger picture, our place in the cosmos, and realizing how amazing it is that we can even explore these questions, these mysteries of the universe. Welcome back. For this final part of our particle physics deep dive, we're switching gears a bit. We've been through the mysteries of the universe, the tiniest particles, the giant experiments, but now it's time for the human side of things.
Yeah, that's a great point. Particle physics isn't just about the theories and the experiments. It's about the people, their passion, their ingenuity, working together all over the world.
It's easy to get lost in the technical stuff, but I always find myself wanting to know more about the people behind it all. What makes them tick? What challenges do they face? How do they manage to work together on these massive projects and actually discover things?
It's pretty inspiring when you think about the scale of some of these projects, like the LHC at CERN, thousands of scientists, engineers, technicians from over 100 countries, all working together trying to figure out the fundamental nature of the universe.
It really is a global effort, everyone united by this shared curiosity. And it's not just the LHC, right? Particle physics research is happening everywhere, with scientists collaborating on all sorts of experiments, neutrino observatories, dark matter detectors, you name it.
Exactly. And that collaborative spirit is essential. Particle physics is complicated.
Yeah.
You need people with different kinds of expertise: theoretical physicists, experimental physicists, data analysts. It takes a whole team to design, build, run these experiments, and then make sense of the data.
It's like this amazing blend of different fields coming together, shows you what humans can achieve when we work together. And it's not just about being smart, right? It takes dedication, patience, and a willingness to wait a long time to see the results.
Absolutely. Some of these experiments take years, even decades, to plan, build, and run. And then analyzing the data can take even longer. It's definitely a long game. You need perseverance.
So it's not just brilliance, it's about grit, that determination to keep going even when the answers aren't clear.
Exactly. But it's incredibly rewarding. There's nothing like that feeling when you discover something new. A piece of the universe's puzzle that no one has ever seen before. It's pure joy, and it makes all that hard work worth it.
It's like being an explorer, charting new territory in the world of knowledge. These particle physicists are like pioneers, going into the unknown and coming back with knowledge that helps us understand the universe and our place in it.
I love that analogy, and it brings up another important point: sharing these discoveries with the rest of the world, making sure people understand how exciting and important this research is.
You're right. Science communication is so important. It's about transparency, about letting people know what we're doing and why. It's about inspiring the next generation of scientists. But it's also about something bigger, I think. It's about sharing the wonder of discovery, the beauty of the universe, showing people that we have this incredible ability to understand these mysteries.
You said it perfectly, and there are so many ways to do that. Documentaries, podcasts like this, interactive exhibits, lectures, even art and music inspired by science. We need to find creative ways to make science engaging and understandable for everyone, no matter who they are.
It's about breaking down the walls between science and the rest of the world, helping people get curious, ask questions, realizing that these discoveries belong to all of us.
Absolutely. The more we can show the connections between particle physics and everyday life, the more people will appreciate how science shapes our understanding of the world.
Well said. Well, here we are, at the end of our particle physics deep dive. We've gone from the tiniest particles to the biggest experiments, from the nitty-gritty details to the stories of the amazing people behind it all. I hope our listeners have come away with a new appreciation for this incredible field, always changing, always pushing the boundaries.
I hope so too. We've explored the standard model, its strengths and weaknesses. We've dug into dark matter, antimatter, those sneaky neutrinos. And we've talked about the mind-blowing technology and the global effort that makes it all possible.
It's been an amazing journey, and we've been so lucky to have you with us, sharing your knowledge and passion for this field.
It's been my pleasure. And remember, this is just the beginning. We've only scratched the surface. There's still so much out there to discover. The future of particle physics is bright, that's for sure.
Absolutely. The universe is full of mysteries, and particle physics is the key to unlocking them. So to our listeners, keep exploring, keep wondering, keep that curiosity alive. The journey of discovery never really ends. Who knows what amazing things we'll find out there.
Thanks for joining us on this incredible deep dive into the world of particle physics. We hope you've enjoyed it.